good evening, everyone. My name is Constantinos Stoumpos. I come from University of Crete. And today I will talk to you about my research on Halide Perovskites. This is my specialty. And first of all, I would like to thank you for the invitation. It's my honor and privilege to be here with you today. And I'm very happy about it. So Halide Perovskites. Perhaps you have heard about Halide Perovskites, perhaps not. So I would like to give you this picture that, in my view, describes collectively the world of Halide Perovskites. Halide Perovskites is a class of semiconductor materials that can be grown into thin films, single crystals, or even micro or nano wires, and or nano crystals in this instance here. And they cover the whole visible range. They can emit in the whole visible range, and they can fine-tune by chemical composition. So you know Halide Perovskites, and the reason you know Halide Perovskites is basically this chart over here. And this chart is the established solar cell performances of materials. Halide Perovskites are here, this curve line. So there was a tremendous progress in the beginning of the field. Now it's starting to stabilize, but again, the performance is very close to that of silicon. So these are good materials to work with, and people are excited about it. But we're plateauing here, we're getting a peak. So why we're looking at these materials? Because there are other applications, and non-applications are radiation detectors, among others. And these are good materials actually for X-ray and hard radiation detection. And some recent work from the group of mercury canadians I had the chance to participate is to grow large single crystal by a Bridgman method and make wafers of this type of material. And we have been able to detect radioactive sources like cobalt or cesium with quite good resolution. That's one example. And other examples why these materials can be useful is this type of microwire I showed you before. These microwires can lace by themselves, and they can lace at a selected wavelength that you can fine-tune by the chemical composition. And we have these crystals have a very, very special property. They have very parallel faces there that act as mirrors, and this they can lace by themselves. Unfortunately, not for a very long time, but that's something that perhaps it's something that we can fix later on. And we can also make the opposite of a solar cell, a photovoltaic device. That's a light emitting device. So you change the injection layer to blocking layers, and then you create an LED device. And we have been able to do that in collaboration with a group of Aditya Mohite, which now is at RISE, formerly Los Alamos National Laboratory. And these are just a few of the properties that we have been involved. Now there are many, many other properties that people are looking at. But I would like to start with from the beginning. And the beginning is the crystal structure. Although I must say I feel very strange to present to you here in Russia about perovskites. Perovskite is Russian in origin, so you must know anything about already. But I will start to describing why perovskites are so important, and in particular halide perovskites. So halide perovskites, unlike the perovskites, the oxides, have a halogen atom in the X position, and this halogen sits in the corner. In the ideal structure, it sits in the corner of a cubic crystal structure with a divalent metal sitting in the middle, and then at the corners of the cube we have the A-side cation, which is basically a non-bonding cation that fills space and balances charges. And you can either describe the perovskite like this or like this. It's equivalent descriptions. But unlike the normal perovskites, you can have a plethora of compositions that you can achieve. For halide perovskite, we have a problem, because we can make this halide perovskite stable only by using three A-side cations. One is cesium, the largest cation in the periodic table. And then, because periodic table is so small, we started doing the same thing with small organic cations. And these cations that can fit in this pocket is the methylammonium cation and the formamidinium cation. And the reason why this is the case is this equation, the Goldsmith tolerance factor equation, which tries to, this is the ionic limit equation, basically considers all the atoms to be ions, and then this is the condition not for the atoms not to touch, and this dictates which structure will be more stable. It has been found that the perovskite structure needs to be in this region. If the A site cation becomes too small, what happens is that the perovskite cavity collapses in, and you form like a different type one-dimensional structure, much less interesting. And if you have the cations to be too large, the cavity opens up, and you get again non-interesting structure, which are only one-dimensional in the lattice expands in one-dimensional in a different way this time. So why would we need to be a perovskite and we're not satisfied with all these other variations? The reason is very simple. The reason is this fantastic electronic band structure that we can obtain from halide perovskites. So you have a huge dispersion, both in the valence band and also in the conduction band. We have huge bandwidth, meaning large mobilities. We have a direct bandgap. And it's also important that unlike most of the perovskite, this dispersion here is also in the valence band is huge. And the reason why we have a huge dispersion coming from the orbital origin of the valence band, which not only contains the halogen orbitals, but also the lone pair, the outer metal orbitals, which are responsible for this dispersion in this portion of the band structure. So halide perovskites, as you know, undergo phase transition, structural phase transition, but depending on temperature or pressure or even composition, you can fine-tune it. And you usually refer to those as alpha phases, meaning that we have the highest possible symmetry, normally cubic symmetry, when the cation is cesium, sphere. Or if we have less symmetrical cations, we have pseudo-tetragonal or pseudo-orthorhombic configuration, and depending on what sits on the pocket PA side point. And these phase transitions are different with temperature for each one of those cations, the three cations I mentioned at the beginning, and can be in phase, where all the octahedra move in the same direction, or out of phase, where every layer of the perovskite shifts in different directions. This is called an out of phase situation. And why we care? Because the tilting angle that connects the metal and the halogen, especially the metal halogen metal bond, it determines the orbital overlap, will effectively decides what the band structure should look like. So for the nearly linear angle, that's the maximum orbital overlap you can have. You turn out to have the smallest bandgap. And this is the case for the alpha formamidine lead iodide. And when you start tilting, what happens is the orbital overlap reduces, and as a result, you have an increase in the bandgap. And if you do it too much, that's the beta methylammonium lead iodide. If you tilt too much, you have another change in the optical absorption. So the optical absorption essentially depends on the angle of the tilting for a given set of compounds, in this instance, lead iodides. So, and we're in this region here. If we go to the other structure, you see the non-perovskitic band structure. You get much larger band gaps with much less interesting electronic structure, like the ones that you will see here. And these are the perovskite band structure as you go from the cubic, tetragonal, and orthorhombic phases. It still retains the basic characteristic, large band dispersion, direct band gap. But if you go to different connectivities, not corner connecting, but either edge sharing or phase sharing, like this one, you get a much less interesting electronic structure. And that's why we want to target this group here. And I would like to say that these types of materials happen with mostly with lead as the bivalent metal, or tin. But there is another metal that we can use from the periodic table, and this is germanium. Germanium perovskites are a little bit special. They have a topology of the perovskite. So the metal and the halogen connects in the same way, but there is a difference in the sense that germanium is not in the center of the octahedron. It's shifted towards one direction along the body diagonal, and this forms a situation where you have a small bonding distance and a larger non-bonding distance. In this case, it is this distance that determines orbital overlap, and if you establish a parameter that connects this distance with this distance, you can find a trend that correlates bandgap depending on the distance between the pyramidal units. And if you plot the electronic band structure, it's still the same. It's very, very similar to the rest of the perovskites. So that means it is connected. There is actual interaction. So it has three-dimensional characteristics. And it can be classified as perovskite. But the important property of the germanium perovskite is not its optoelectronic properties, rather the fact that it lacks an inversion symmetry. And this lack of inversion symmetry can be established by second harmonic generation measurement, which show that it has a very strong response. And if you compare with a known material like silver gallium sulfide, you get a polarizability coefficient, a Chi2 coefficient, which is approximately 1 order of magnitude higher than common materials. So this is the big benefit in this material. Potentially, these materials could be ferroelectrics, never measured so far. But the reason is that they have quite large conductivity, and so the measurement itself is really difficult. But they also have another property, which we first found by doing high-pressure measurements in these materials. And high-pressure measurements shows a very large change in the energy gap as a function of pressure, as you see here. Like various pressures, you see how the bandgap narrows significantly. And we realized that after some pressure thresholds, whereas you don't have very strong photoluminescence properties, basically zero, after you apply pressure to an extent, you start having the material shine light. And inspired by the high pressure experiments, we did also the chemical pressure experiment. Namely, we substituted cesium for methylammonium throughout the series. And while cesium emits like very strongly at its bandgap, methylammonium doesn't, we can fine-tune it continuously by triggering the photoluminescent threshold. And we found that there is a special rate for a special separation for the octahedra and the pyramids, so that we can trigger photoluminescence to appear. So that's a very interesting story. We don't quite understand, or we speculate a lot on this. I would like to have your opinion too on why this is so, but this is what experiment suggests. And with this, I'm finishing the presentation of the perovskites, and I would like to get to the properties. What's so special about perovskite? Perovskite have a very special property, which to me was eye-opening when I started looking into this material. Basically, that you can synthesize the same compound with a different method and produce a material with different properties. And using this simple reaction, I get a tin iodide, I synthesize tin iodides, I react it with an iodide salt, and you make the perovskite. It is as simple as that. You can do it mechanically, simply by grinding. You can melt it to form ingots, and you can also grow these crystals from solution. Each and every method gives different properties. So for example, if you melt it, you get a very intense photoluminescence. Typically, if you measure electrical properties, you are on the p-type doped, self-doped region. If you make it from solution, you are on the n-type side, and the photoluminescence is much decreased. And trying to analyze these properties, we try to compare our data, our resistivity data, with the data that have been published in the open literature. And we find out that we are approximately 4 orders of magnitude higher in the resistivity compared to the literature or previous attempts, simply because we're using something that prevents self-oxidation of the metal. Tin has a very, very special property. When it oxidizes and it goes from the 2+ state to the 4+ state, to maintain the same coordination environment. That means the structure remains roughly the same, so it's very easy to oxidize. But you need to take very special care, and we use this reducing agent to revert the oxidation from 4+ from 2+ to 4+, which is responsible for the p-type doping in the material. And we managed to keep it to as low threshold as possible, obtaining large mobilities. So the numbers are not very accurate, but because the difficulty is actually very difficult to make, these materials are extremely sensitive to handle. But still, we have been able to demonstrate that there is some large difference from the use of reducing agent or not. And another unique property of the perovskites, one is this. The second unique property is that the structure that you see is not actually there. What I told you so far, it's a lie. Or not so. Basically, when we're doing crystallography, we're looking at the average position. But the atoms are vibrating very aggressively. The octahedra are moving. So basically, they're in constant motion and at room temperature. You can see that by the large ellipsoids having this motion and this shape. They're flat, pancake-like, so meaning that the octahedra are moving. So they're continuously disordered, but the average position is exactly where you expect on a perovskite. That can be seen by the shrinking of the thermal ellipsoid by crystallography as we lower the temperature. This is normal, until you get a temperature that the atoms freeze and they finally are in the position you think they are. And the way to do this and prove it, because crystallographically this is impossible to do, we do Raman spectroscopy. And if you try to follow the Raman spectra, in this situation, the dynamically disordered situation, and this situation, you see that the Raman spectrum suddenly appears once the atoms freeze, and you have normal vibrations. And this is generic for either for cesium or methylammonium, it doesn't matter. What matters, what changes is the temperature that you see this effect. And this has also a consequence on the properties, because if you we try to compare with classical semiconductors in terms of what happens, what the effect is that the temperature has on the optical bandgap and also the thermal coefficient, because we want to know what happens to the lattice. We see that we have a massive thermal expansion coefficient, volumetric coefficient, much larger than what we expect for the classical semiconductors. And we also have an increase in the bandgap as we increase the temperature, contrary to what we see for normal semiconductors. And we try to analyze this property. It's a consequence of this dynamic disorder that I described just before. And to do this, we had to do total scattering experiments. So to try to correlate direct space with possible deviations from the original position. So we're looking at the movement of the central atom of the octahedral from its position at the center of the octahedron. And basically you see that there is some shifting. We see a peak, a shoulder happening at a different distance between the metal and the halogen. And it varies for every of the perovskite we selected from close to 0 when we're on the lead side, to large deformation when we go to other metals, especially tin and different cations. And all these properties, this is a phenomenon that Mercury Kanadzidis, when he was working with lead chalcogenides, termed emphanesis, meaning appearance. There is a solder appearing here, a second distance in the proximity of the metal ion. This is the deformation of the octahedron. And its response, it all goes back simply to the nature of the orbitals on top of the valence band. This is what changes with temperature. And if I remember in the beginning, I told you that this has a contribution. These orbitals at the top of the valence band have contribution from the s orbitals of the metal. So the metal plays a role in the valence band. And this is what shifts up and down as you change the temperature, from delocalized to localized. And this changes also the dispersion on top of the valence band. And this is responsible for all these properties. And how do we know? There are calculations substituting calcium with tin. Calcium doesn't have this contribution, tin has it. And you see that clearly there is a significant change in the trend of the valence band. And by applying pressure or deformation, this is an effect of the temperature based on thermal expansion. So, different concepts. So we are limited, right? I told you before that we are limited by composition. We have 3 cations, 3 metals, and 3 halogens. So what to do to go about it? We do chemistry, and we apply the dimensional reduction principle. Basically, we get the 3-dimensional material, and you slice it, or drill it, slice it into layers, wires, and so on. And we can do this by using simple chemistry. And if you start with this lattice, I talked to you about the phase transition, there are possibilities. What will happen if you try intermediate size cations? Is it possible to do chemistry? The answer is yes. And for the case of tin, for example, if you try this selection of small cations that may closely fit or slightly off, you end up with a palette of materials going from the perovskite black phases to yellow phases. Sorry about the color here. And you get a palette. You don't get the same thing. It's not black and white, perovskite or non-perovskite. Instead, if you visualize that we have a perovskite that looks like this, we can use some cations that retain the characteristic of the perovskite and either slice the perovskite. For example, if you will use isopropyl ammonium or vanadium, you get this structure. But each cation will slice the perovskite in different direction, in different crystallographic direction, either in 100 or 110. And these numbers refer to the ideal cubic structure. And there is a special case that along the 111 direction, you can have either phase sharing or corner sharing, and you can have combination of these two connectivities. This is the category of hexagonal polytypes. And you can have as many of those corner connections and phase sharing connections. This is known for oxide perovskites, but you can also do it for halide perovskites as well. And if you conceptualize how this is happening, essentially you get a perfect perovskite and you start removing metal ions and replacing them by the large cation. And this has a strong impact on the optical properties. This is the perfect perovskite, and you see how much you change the optical properties when you go through the several cations. So this may or may not be interesting. These materials have not been seriously looked at, but we know that they have some similar characteristics with the other perovskites. And then we end up with this strange cation, ethylene diammonium. And when we do the same experiment, instead of changing the structure of not going or having a different structure type, what happens is when you start adding this into the solution, you see a color change. Actually, a black material can turn red, meaning that there is a huge increase in the optical absorption in the bandgap, but the structure doesn't change. So the crystal structure is exactly the same. How is this possible? So that's a mystery. And we can also see that ethylene diammonium is incorporated into the structure. We do this by NMR spectroscopy. You also see the bandgap, and it has all the characteristics. What's going on? So this has also, other than the optical properties, there are some secondary effects. So for example, you change a typical morphology of the crystals, like this, to this. So basically, you know that somehow it is incorporated. But the most compelling experiment, from my point of view, is that if you actually measure experimentally the density of the crystals that you produce, you see that there is a very significant loss, a change in the density. So a normal density is around 4 for the perfect perovskite, and then you can end up with a density of 3.5. So the organic cation goes in. Where? We're not sure yet. And we're not sure exactly what goes out, because it's impossible. The charge, remember, the charge is 2+, as opposed to the A-side cation, which is 1+. So something must go away. And we simply make an artificial crystal structure by removing octahedra, the unit cell. And when you do that and do the band structure analysis, what we see is that actually missing octahedra will clearly increase the bandgap if you compare this opening here with this opening here. And we made this cartoon model. But to strengthen our argument, let me skip this, I will come back later. To strengthen our argument, basically we did again total scattering, and we're trying to see the correlation between lead-lead and iodide-iodide interactions. We see that iodide-iodide interactions don't change from the pristine material compared to the loaded with ethylene diamine material. But what changes significantly is the correlation between the lead atoms. That, to my eye, suggests that this correlation suggests that ethylene diamine actually replaces the metal rather than the cation. And this is how we end up with a scenario that we drill holes in the perovskite. And we tend to, because we cannot see these holes in this system, we call this type of materials hollow perovskite or disordered hollow perovskite. And this model clearly shows up if we use this cation, +1 cation, we just change this part. The charge matches now, and you can clearly see the crystal structure forming holes with missing octahedra. So these are the ordered hollow perovskite. This is a work by Nicolas Mercier at Angers in France. So, and I would like to, I don't know how much time we have now to start a new, okay, I think we're good with time. The second part, and I would think this is the most interesting part, what happens if we make slices? We make two-dimensional perovskites. Two-dimensional materials are very popular, and this is where we started. This is the original work by Hema Mala Karuna Dasha at Stanford, and she was the first person to try to make two-dimensional perovskites in layers, in tri-layers, and having this compound over here. This is old compound studied from the 80s and the 90s, and she applied this material for solar cells. And one thing that struck me, and this is how I started looking into this system, is that whereas for the three-dimensional perovskite, for the bulk of the perovskite, we have a very nice clean absorption. In the case of these materials, when you synthesize the crystal, dissolve in a solution, and try to make a film for a solar cell, you see a picture that looks like this. Steps. This cannot be a clean material, obviously. this corresponds probably to discrete absorption coming from discrete materials. So, and also keep in mind that George Papavasiliou, back in the 90s, stated that if you try to make compounds of this formula, and I'll explain how this formula works in a minute, you cannot synthesize materials with n, which is the number of layers. N corresponds to the number of layers. So this would be 1, 2, 3 layers. Cannot be made in a pure form. That was a statement. And to me, that was a trigger. I wanted to know why. And that's how we set up doing this synthesis. We went into the lab and we synthesized materials, not these exact materials, but similar ones. And basically, these materials belong to the homologous series, where you have the butyl ammonium, these longer molecules. Obviously, this cannot fit in the cavity. And it separates the layers one by one. But if you choose the stoichiometry of the chemical reaction carefully, you are able to isolate the materials in pure form, and you can essentially control the optical properties. And once you have this done, we have been able to solve the crystal structure. Look how these materials actually look like. And you can go from the monolayer to the bilayer to the trilayer to the tetralayer, and so on. And you can actually predict what you expect to see by this kind of reactions, because you know that the dimensions of the unit cell should stay exactly the same, and the only thing that changes is this spacer, the molecular scissors that you use to separate the layers. And butyl ammonium is an effective one, the most well-studied so far. And we know exactly, we can predict actually the size of the unit cell. And just to convince you that this is not one crystal, that I wish all the secret structure and we're lucky to get it right, this is how the powder diffraction spectra look like. The materials are chemically pure, and that's the important part. If you want to do application of any kind, you need to make the material pure. That's from the chemistry perspective, this is what you need for anybody to believe you. And you will see that you have like perfect ordering. Interestingly, the number of small peaks below the peak of the bulk phase actually give you the number of layers. So you have 4 peaks here, you have 4 layers, 3 peaks, 3 layers, and so on. That's accidental, by the way. But it's very helpful when you try to characterize the materials. And we went even further. We synthesized the 5-layer perovskite. This is how the simulated reciprocal space would look like for this type of materials. And can go even further. We were mapping how high we can go. We're a little bit looking at the limits of the system. And we found that above 5, we can actually see diffraction peaks that correspond to these higher layers. But it was very difficult to get them pure, because if you compare with the 3-dimensional perovskite here, you'll see that there is always impurity from the 3-dimension. To some extent, these materials become 3-dimensional. And they are impure, so difficult to acquire the properties of these materials. And we continued, though, and tried to solve some structures, and we hold the record now. 7-layer perovskite. These are massive unit cells. The unit cell itself is 10 nanometers. This layer is 5 nanometers to have a scale. And we see that as we go so high in thickness, we're approximating the optical properties of the bulk perovskite. And another interesting work we did with Alexander Anavrosky and Santiago, we did the thermochemistry, and we found out that actually the enthalpy of formation differs depending on the fact that whether the number of inorganic layers is odd or even. And we see for this particular set of butyl ammonium perovskites, it's much more stable to stabilize n equals to 2 and 4 layers, as opposed to 3 and 5. Ignore this part, this probably is a measurement wrong. You cannot go above the formation enthalpy of the 3-dimensional perovskite. But there is some correlation, because if you look at the symmetry, yes, this is the mirror plane separating the the two sides of the layer in this case, and here it's a glide plane. So this is symmetric, this is not so symmetric. So it could be the reason, but we need more experiments in this direction to find out why this is the case. So, but overall, let me come back to the original question. Is the original work by Hema, Malekar, and Dasa the spectrum corresponding to a single compound? And the answer is no. And we know that now because we are 100% sure that we have the pure materials, and as such, we have been able to obtain from each member the optical properties. And you see that each of these discrete modes in that original spectra corresponds to a palette, a mixture of all these individual states, emissions that come as a result of quantum confinement and spatial dielectric confinement from these materials. And there is this work by our colleagues in Los Alamos who studied extensively and tried to get the evolution, the effect of quantum confinement. It's not a simple quantum confinement. There is a very significant contribution from the dielectric contrast between the organic and the inorganic part. So we found an equation that may or may not hold. I just wanted to stress that these materials have huge binding energies, and we're talking here about room temperature measurements, all these measurements at room temperature. And this is something that intrigues us and try to understand it better. So from the band structure point of view, band structure look like this. So if you consider this version of the three-dimensional perovskite, it should look like this. And what actually happens electronically is we break the valence band and conduction band extrema into states, and the number of states that we break them into correspond to the number of layers. This is the N=5 perovskite. I forgot to say 5-layer perovskite. And what is interesting, but I'm not sure at this point if this is an artifact from the DFT calculation or not, is that valence band seems to localize in the middle layers, 2 and 4, the second and the fourth layer of the quintuplet, but the conduction band localizes at the edges. And if this holds, it may have consequences because you need to know where we get to put an electron acceptor or an electron donor to collect electrons for devices. This hasn't been proven, it's just a picture at the moment. And just to give you a measure, we had this recently, we published this paper, and just to give a comparison where we are. This is a massive binding energy, much larger than many materials. And if you want to compare it with something, you would compare it with some organic electronic materials. So, interesting materials, if you agree with me. So we need to make devices. To make devices, you need to cast them into films. That's the original trouble that Hema, Malekar, and Dasa had in the original work. And we had the same problem. So you want to make solar cell devices, you want the electrons to flow through the materials from electrode to electrode. So normally, if you cast a two-dimensional perovskite on a surface, you expect the lattice to expand in the plane. And that's actually the case, it does, for the monolayer. And it also does for the tri-layer if you use some special treatment. But when you start thickening the perovskite, you get some different orientation also appearing. So instead of laying flat, you get some flat component, you get some perpendicular component. But when you go to the 3 layers, you only see the perpendicular component. So basically, the layers are growing perpendicular to the substrate. That's interesting and useful because you extend the lattice from electrode to electrode. This is where you want to be. And why this is happening is still unclear, but it's certainly beneficial to make devices. And we did make devices. Originally, we didn't get such good devices. I must admit, it was the mesoporous architecture that we used. We get up to 4% for the 3 layers. But then, again, we collaborated with a group of Aditya Mohite at Los Alamos. And by using a planar architecture and his patent hot casting technique, we have been able to get 12% efficiency. And that was the record efficiency at the time with good consistency in the conversion efficiency. This is much smaller than the 3D perovskite, but it has other benefits. For example, you have a lot of organic content within this material, and this protects it from water. Water kills these perovskites. And this is the picture, the picture that we want to for you to imagine. But we, by GWAX experiments, actually show that the method is important. When you are able to grow large grains of the material on the film, you are able to get high efficiencies as opposed to the polycrystalline film here. And another effect that we saw when we're trying, we didn't name it or we didn't address it at this time, but we address it later on. When you cast the perovskite on the film, no matter how pure it is in its single crystalline form, and you see this is reproducible what I showed you before. This is the emission on exfoliated crystal, clean crystals. When you go and cast it on and measure the same properties on a film, it's not the same. And the most characteristic example happened for this crystal, the n equals 2 example. So you have a single crystal, you have this emission here, and you get a film, you have an emission here for the exact same composition. And if you get a crystal that is damaged, or bad crystal, or the edge of the crystal, you see both emissions. Both the emissions that will correspond to the free exciton and the emission that will correspond to this state, trap-like state. And these trap-like states have much longer lifetime compared to the free exciton, as expected. And nobody knows why this is happening, but my personal guess is that if we run back to what happens in oxide when you try to grow multiple layers, and this is a 10-layer perovskite grown for strontium titanate, you see that the layers at higher thickness, this is 5 layers, this is 10 layers, this is the record, by the way, of all perovskite in general, you see that there are defects and deficiencies. Essentially, you have 10-layer thick materials that can actually connect with one another and grow much larger, 3D-like, bulk-like materials. So I think this is what's going on here, although it's very difficult to visualize this material by TEM spectroscopy, and simply because you actually burn them, the electron beam will burn them. But this is an interesting challenge for the future. So over the years, perovskites branch out a lot. So we can have different categories of perovskites. And many spacer cations have been used in between, donors, acceptors, different functional groups. There is a lot of work that has been done, and they have been able to obtain many variations of these perovskites, of these layered perovskites, from step-like, as we call them, from single cation perovskites where the spacer and the perovskitizer, the cation that is responsible for the formation of the perovskite cavity, is the same. There are many examples. And depending on how much time I have, I will give you some examples, if it's okay. Yeah, all right. So one example, what we can play with is the length of the chain. You would imagine in a quantum well, you want to adjust the properties by tuning the length of the well and the barrier. And in this case, okay, if you go too small, and going too small is important because we want to have electronic communication between the layers. What happens is you break the structure, it doesn't fall. But if you go too large, like by increasing the carbon atoms in the carbon chain, basically what you see is exactly the same effect. You see the discrete emissions at specific wavelengths that depends only on the barrier, only on the well thickness, but not on the barrier. You can have them 1 angstrom, 2 angstrom, 3 angstrom different, nothing happens. So it's not important. And that's interesting. So somehow the barrier doesn't play a role. It's only on the inorganic part that is important. So what you can actually do from the chemistry perspective is change the chemistry of what you place here. What you can do in the 3D perovskite, you can do it in the 2D perovskite by playing with the contents of the cavity. And you can have this whole palette from undistorted to distorted, in plane or out of plane, by playing with this set of cations. This would be the spacer, and playing with the two perovskitizers, methylammonium and fluorinaridinium. You are able to adjust the properties within the bilayer, because all these have been tried for a bilayer perovskite. So there is a lot of chemistry here that we can do and fine-tune a little bit the excitonic properties from undistorted to distorted. But there is a lot of work that can be done here, and that's my favorite part. You can change the offsets of the layers. For example, in the original case I showed you, the perovskites are the two layers are offset by half an octahedron, so that this octahedron fits exactly in this pocket. Other types, like for example the Dion-Jacobson type, where you use 2+ cation, not a +1, 2 monocations, but a 2+ cation, so you can bring the layers closer together, and one on top of the other. And this is also this strange combination where you use 2 cations in the layer, and they fill different pockets. This is alternating cation in the interlayer space. Not the most brilliant name, but it describes the situation. And this one, together with this one, bring the layers closer together. And this is the search for two-dimensional perovskite that have actual communication between the layers. So we want to break the infinite well. And this is how this conformation would look like, and why we care. Because for a given set of layers, this change in the 3 types of perovskite can give significantly different properties in the sequence as you build the layers. And the origin, potentially, can be the energy difference associated with communication, electronic communication between the layers. Again, there is no definitive proof about that, but we have experimental data that we understand that there is actually a difference in the energy level, despite the well length being the same. So I would like to conclude, or I hope I convinced you, about halide perovskites being nice, interesting materials. And I would like to thank the people that actually contributed to this work. And most of what I showed you so far come from my work with a group of Professor Karnatsidis. And I would like to thank specific people who were very helpful in this work: Ling Mao, Chen Mei, Kyle McCall, and Dana Kao here, and also Wei Junke. All these students are now professors in universities. And I would also like to thank the collaboration of the big heads behind this work: Ramses Adri, Aditya Mohide, and Zaki Iven in Trent. Many collaboration, of course. And after that, I would like to show where I stand. So in 2018, I started my independent work at University of Crete. I started the crystal chemistry laboratory, and this is the group. And what we are doing is try to work on solar cells, set up facilities for solar cells in Crete, which were not there before, difficult task. And we do crystal growth, and we study dielectric spectroscopy. We are looking for polaritons with this material. And this is a big challenge, because I told you it's interesting. We want to have like clean materials, but we also want to avoid these edge effects. So this is quite a challenging task to have these crystals and cavities, but we have some successes so far. We do exploratory synthesis, or actually targeted synthesis. So far, I talked about iodide chemistry. Nobody has looked into the bromide. This is something we're interested at. We try to optimize this. We do lots of exploratory synthesis from monochromatic to white light emission. We also study thermodynamics of these materials. And we look into lead-free perovskites, which is a big thing in literature because nobody likes lead somehow. We do a little bit of crystallography, modulated structures. There are actually some modulated structures in these systems, and we try to understand the structure property consequences in this type of systems. And we also started to do some machine learning, try to predict materials and then go to the lab and synthesize it. And that's all about me. I would like to say a few words about the laboratory we're setting up here, together with Professor Alexei Emelin and Dr. Yuri Kapiton. We're setting up a lab, crystal photonics. We make the crystals, and now from these crystals, we're going to study properties, laboratory of crystal photonics, or laboratory of crystal photonic, if I'm not very wrong with the pronunciation. And we're actually hiring. So we're interested to set up a lab to, from the synthesis viewpoint, start making these materials and characterize them. And that will be the goal of this new laboratory we are setting up. So if you are interested in joining the group, please send us your CVs. We will evaluate them, and we are happy to accept you in the group. And about the locations, we're at Peterhof, the fourth building of Institute of Photonics. We will have a website soon. And the topics we will be dealing with are basically perovskite related, but we're open. We are doing research of any kind of materials. We have experience, we have the will to study new materials, and we are very, very interested to study their optical properties. And with this, I would like to thank you for your attention here and online, and I'm happy to take questions.
Thank you very much for a very nice presentation of Constantinos. Maybe somebody has questions. Please, you're welcome.
And you presented many results on optical characterization, like the absorption or luminescence. And how about the electrical properties? What is the main dopant as far as when there's a wide gap? Really, semiconductors are needed to be doped. Yeah, what is known about what the highest level of doping it is possible to create P and N type, and what is electron and hole mobility and so on?
Yeah, I have an answer for this. And that's a very good question. Normally, when you think about semiconductors, you think doping. Yeah, perovskites cannot be doped. And because they are ternary systems. And because they are ternary systems, let's say you try to dope the B side, the metal side, then you will lose some of the A side to compensate. But it will not dope electrically. It will lose the cation. So it will lose the ion and it's happy, no doping. Same goes for the halogen. If you try to change the halogen, no, again, it will compensate for the other side. So you cannot dope it intentionally. And people have tried to dope it. Electrical properties do not change in general. And the case I showed you for tin, when you have the tin as the metal side, it happens because tin oxidizes in air by itself. And that's the reason also why this material is very sensitive. So if you leave it for 5 minutes in air, it will oxidize, it will dope, but after some time it will be destroyed from another compound. So it's very fine-tuning, but intentionally, you can only change the oxidation state of the metal. So electrical properties are difficult to control. But in the case of tin, we have been able actually to dope P and N type, but it's very, very difficult. It needs fine control. And let me go back to the slide for this. Yeah, it's been way back. Sorry about that. Can I go faster way? Can maybe I can get out of the presentation. So what is going on is that normally tin has the tendency to dope p-type by itself because of its self-oxidation. But if you stop the self-oxidation, if you block it, then you can make a perfect material without defects, which is merely intrinsic, but on the N-type side. But the mobilities, I mean, if you ask me what mobilities I measure more than 1,000, but I don't believe that number. I would like to believe it was a wrong measurement. It's a very difficult measurement. But for lead that cannot be doped, for example, you get a mobility around in the order of 100 centimeters square volt second. For lead. For tin, it can go higher. I will still not get it. But I hope I answered the question.
What is really then we need really rather shallow stains at the band gap to achieve high electrical conductivity. And what is known about this defects is you introduced using different stages of oxidation.
Yeah, this is a typical conductivity for this material. As made, pristine. Okay, sorry, it reads, okay, at room temperature should be about 10 to the minus 4 by the 10 to the minus 2 ohm centimeter. But what I can get, it's probably 2 to 3 orders of magnitude higher. And by using simply this one, when I make the crystals, because these are crystals made from solution, it's basically this type of crystals. So if you use this reducing agents, you prevent oxidation, and that's how you get it to be N-type. I mean, N-type, how much? It's unclear, and it changes from synthesis to synthesis. It's hard to control, but you change the behavior at least. You change from this temperature activation to this. It's hard.
Yeah. Okay, this is 3D materials, and how about this your 2D materials? It's
2D materials,
really very interesting. Would be
This for the tin materials, no, it has been done actually in 1994 by David Mitchell. There is a famous paper in Nature that he does that, and he says that as you increase the layer, you go P-type. If you decrease it, you go N-type. So it's a function of, it's very interesting, but difficult to study and worth looking at further in the future, I agree.
Okay, some other questions?
Peter Tolstoy from the Institute of Chemistry. Could you please comment on what are the typical timescales of the rotational dynamics? Doing some. Okay. What are the typical timescales of the rotational dynamics of the organic cation? And why everyone is using the ammonium cation, though chemically one can imagine a bunch of different ones, from pyridinium, imidazolium, phosphonium. There are many different sources of the positive charge in organic chemistry.
Okay, this can be done. It's a size question, size and shape, right? Methylammonium is just suitable size to replace. For vanadium, yes. If you go slightly more, acetamidium, vanadium, no, it forms these polytypes I showed you. It doesn't want to fit. It doesn't fit good enough. But I think that for methyl phosphonium, it has been done, although very few groups can use methyl phosphonium without catching fire. So I guess that's one of the reasons. It's possible, yeah. I don't see the chemical reason not to be able to do that. And the second question is the rotation. There actually works from the 90s that say it's in the order of megahertz rotation frequencies. They studied by NMR. And it's also frequency temperature dependent. As I showed you, these are dynamically disordered systems. And you have changes in the mechanism as you go from this phase to this phase to this phase. So the rotation happens like thermally or by tunneling. There is a tunneling mechanism. But they study this by solid state NMR. I'm not involved with NMR. I would like to. I don't have a chance, never had the chance, but I think it's a really interesting experiment to do because NMR looks at time scales that are that will give you a lot of information about the rotation.
Just one little comment at the end. As I'm personally an NMR spectroscopist, we definitely should do this experiment. So we will definitely meet again on this topic.
Yeah, I'll be very happy to.
Okay, thank you. Other questions? I don't see anybody. May I ask anything? You see, the first question is not scientific. I was deeply impressed by the number of papers published by your laboratory. And am I right that your huge factor is about 77 years?
No, I don't want to keep track, but yeah, it's about right, yes.
Okay, so for what I wanted to ask about science, you have shown some results for Raman spectroscopy, and what could be done using, for example, infrared, if you plan anything like that?
Well, I would happy to. I mean, it's complementary. Infrared is complementary to Raman. The problem is that infrared measures absolute energies, and if you look at the phonons, if you look at the frequencies, the phonon frequencies for the systems are in the order of 100, from 50 to 100 reciprocal centimeters. It's difficult energies to get by infrared, far infrared. I think so. I mean, when I tried with a standard instrumentation, the Nicolette instrument, I couldn't reach them. It was just noise in the spectrum.
Okay, thank you. We can discuss it later, perhaps.
Yeah,
thank you.
If you can solve this problem, then it would be a fantastic tool, I have to say.
Other questions? It seems that there are no questions. So once again, we would like to thank you for your very interesting presentation. And see you again.
Thank you for the invitation again.